So this problem says if A is an ideal of the ring R, which we're assuming to be a commutative ring with unity when we're talking about ideals. You can talk about ideals, one-sided ideals in rings that are not commutative, but to keep things simple, in our class, we assume the ring is commutative. And one, the unity is in A. The conclusion is that A equals R. In other words, the only non-trivial ideal of R containing the unity is R itself. Well, actually, that would be a non-proper ideal, but it's also non-trivial if R itself is non-trivial. Kind of a weird result. If this one element is an R, if the unity, this one element is an A, then A equals all of R. But certainly, A is a subset of R, right? It's a subring. Ideals, in case you've forgotten, are subrings. They're closed under addition and subtraction. They're closed under multiplication. They're also, being an ideal, what I call superclosed. Got some element in the ideal and you multiply it by some arbitrary element of the ring, the product is still in the ideal. It gets sucked in there. So we must show the other inclusion, that R is a subset of A. Give me an arbitrary element of R. Why is it an A? Always remember, when you're doing proofs like this, you got to use what you're assuming. Somehow we've got to use the fact that the unity is in there. Just a little bit of experimentation. I hope you realized, okay, maybe I should write R as R times 1. And then, again, the ideal, by definition, is superclosed. Arbitrary ring element times an element of the ideal, by definition of an ideal, is in the ideal. So it's essentially since 1 is in the ideal, by definition of ideal. This is pretty useful result, actually. Anytime you know the unity is in the ideal actually has to be all of R. It's pretty useful. The next problem uses this result. It states if I is an ideal of R containing a unit, meaning an element with a multiplicative inverse, then in fact, I is all of R. Once again, I being a subset of R is trivial. That's trivial because it's a subring being an ideal. So once again, you've got to just show that the entire ring is in fact a subset of the ideal. You could try to do that by with set inclusion, but you also can just use number 19. If we can show that 1 is in the ideal, then we can invoke the previous problem to say the ideal is all of R. So you don't really have to show the inclusion, actually. You can just invoke number 19, the previous problem. And so how do you show 1 is in there? Well, I contains a unit. So let R in I be a unit. That implies it's got a multiplicative inverse. There exists an R inverse in the ring. Maybe in the ideal, maybe not. A priori, you don't know. It actually will be in the ideal, but such that R times R inverse is 1, the unity, right? Or said another way, 1 is R times R inverse. But the ideal is superclosed. This element is in the ideal. R is in the ideal. Therefore, the product of something in the ideal with any other ring element is in the ideal. Again, I call that superclosure. That's not a standard word. Therefore, I equals R by the previous problem. Number 19 in the book.